Cool. Hi, my name is Giannoulis. I used to study here. I did math. Had a great time doing it. Had a great time with sums. So I thought I'd come back and give an upgraded version of a talk I gave, geez, I don't know how many years ago now, 2 years ago. If you saw the last one, the proofs in this one I think are a little bit clearer. They're certainly more rigorous. And there's an added kind of afterthought, which is just a little bit of talk about what it means for something to converge almost surely, and how we really think about probability in infinite sample spaces. So we'll get to that. So, quick summary of the talk. So I guess this is just a glossary page, but the main result of this talk will be that a certain sequence of pieces, if you encounter it, will end your game. And then we also showed that the probability that you would eventually see the sequence of pieces is 1. So you are eventually going to see the sequence. When you see the sequence, you're not going to be able to do anything about it. The game's over. So this is the sequence in question. So it's an S piece and a Z piece, or however you want to think about those two pieces, alternating this many times, where H is the height of the board, but we'll get to that in a minute. Anyway, Tetris. Okay, so just some ground rules for anyone who might not know how Tetris is played or what it is. I hope that's not too many people. So a Tetris board is a rectangular group of squares with a width of 10. So we're gonna fix the width of 10. But just as an interesting addendum, we can have the board with any number which is congruent to 2 mod 4. Why is that? So just a quick explanation of that. The fact that it's congruent to 2 mod 4 means that A is even. So first of all, we can write it as such in the form of 4k plus 2. We want it to be even, because we do want an even number of with 2 columns. So we factor out a 2, and now we have 2k plus 1. But this is critical. The number of width 2 columns has to be odd for this proof to work. Okay. So, players must place falling pieces, which are called tetrominoes. I'll show you the tetrominoes afterwards, on the board. So the pieces fall down, you have to maneuver the pieces and place them. Pieces may be rotated 90 degrees and shifted left and right until they land. And so when I say they may be rotated 90 degrees, you can do this iteratively, so it's not only one rotation allowed, you can rotate as many times as you like. I'm sure everyone knows how to play Tetris. Sorry, I say rotations are not allowed, I mean reflections. Reflections are not allowed, so we will assume that when you're given a piece, you may not change the orientation of the piece. Change rotation orientation, but not the left and right orientation. Full rows are deleted after every placement. So when a row is full of squares that have been placed, the row is deleted, and the rows above it just are shifted down. A game ends if a placed piece reaches the ceiling. So these are the tetrominoes. This is an incomplete set of the tetrominoes. Can anyone tell me why? Not that many people will ask.
Yeah, reflections.
Yes. So in particular, the orange piece there has a reflection that is emitted, and the green piece there has a reflection which is emitted. So there are 7 pieces, not 5. Losing games. So call an infinite sequence of tetrominoes a game. So in particular, a game in my mind is defined by the pieces you're given, because the board is pretty much fixed. And so, you might have a sequence which looks like, you get a square, and then you get a rectangular piece, and then you get one of these 3 pieces, and then maybe you get another square, and the game goes on infinitely, right? So it's just the pieces you get in the game. We will call a game and a board lost if there is no strategy to play indefinitely. So if we cannot place all the pieces in such a way that we never break the ceilings, like if there is no infinite strategy to place the infinite pieces, then the game is lost. Okay. Cool. Yeah. So the main theorem of this talk, it's like the main thing we present. For a board of any height, so we'll call the height H, any game which contains the finite sequence gamma is a losing game. And so I haven't included it on the slide, so I hope you can see this. The sequence gamma is given by this. So it's this alternating sequence of S and Z pieces with this many repetitions, where H is the height of the board. Okay? So I know this is a little bit arcane. Where on earth does this come from, this number? Maybe you can see why this sequence is a losing game. Nobody's very happy to see, a string of these pieces crop up indefinitely. It's not fun. But in fact, it's so not fun that you will lose the game. And we'll derive that along the way. Oh, just to be clear, we don't mention H is the height of the board. Okay, so we begin with the lemma. So first we begin with this odd placement lemma. So on a board of height h with a game containing gamma, so we say a game contains gamma if a finite subsequence is gamma. So if we look at it as an infinite sequence, we can look at finite sequences, which are, however many pieces in a row, and we'll say a sequence contains gamma if it has a finite subsequence, which is gamma. So on a board of height h with a game containing gamma as a subsequence, no more than 30 h pieces may be placed either horizontally, that is, like this or like this, or with their leftmost cells in an even-numbered column of the board after the commencement of gamma. So I know that sounds a little bit strange, so I'll just be very clear about what I mean. So if we have some kind of board with some columns, we're only allowing a finite. So this is a horizontal placement. And as far as the column numberings go, so this is 1, 2, 3, 4. When we place a piece vertically, we will say that its leftmost piece is in an even numbered column if it looks something like this. Okay, so if it's placed vertically, and as left as it goes, it's in an even column. Okay, so this is a bit of a strange seeming lemma, so I'll just kind of give some motivation for it. The idea is that it's hard to keep placing pieces horizontally because the length of a horizontally placed piece is 3. And there are 10 columns, so you end up with these issues where you're going to leave some kind of column on the side that is unfilled, which is problematic. Similarly, if we place pieces vertically such that their leftmost pieces are in an even numbered column, then, well, if you try to fill that out, then you end up with this problem where, again, you must leave a column somewhere, maybe on the side. So if you had it here, then you'd be leaving this column here on the side. So that's kind of some motivation for how you'd be placing these S and Z if you were trying to survive, but it's not enough. So now we'll show that this is not possible. Well, that you can't place more of these. It's not enough. So here's the proof. Unfortunately, this is a part of the talk where the algebra does get a little bit messy, but hopefully it shouldn't be too hard to follow. So we will let di be the number of squares placed in column I before gamma. So what I mean by that is that the game is played. At some point, we reach the sequence gamma, and I'm saying if you look at the state of the board, assuming the game hasn't ended, you're looking at some number of squares in each column. Okay? We don't care how they're distributed, if there are holes. We just want to know how many squares are there in each column, and that's going to be di. So to be clear, d1 will denote the number of squares in column 1, di is the number of squares in column I. Let bi be the number of squares we've placed in column I sometime during gamma. So now we're in the sequence gamma, we've been placing pieces, and at some point we have placed, of pieces from gamma, we've placed b1 squares in column 1, bi squares in column I. Let hi be the number of horizontal pieces from gamma placed with center in column I. So going back to this horribly messy now diagram, a piece placed like this, has its center in 2, so we'll denote it, this will contribute to H2. And lastly, we have vi, the number of vertical places from gamma placed with leftmost squares in I. Okay. So again, as last time, I'm not even going to explain this one. The point is that if the leftmost square is in column I, we count it in vi. So now the result we're trying to prove becomes the following. We would like to prove that I equals 1 to 10 h. So the number of horizontally placed pieces. So this is the number of horizontally placed pieces. This is the number of vertically placed pieces with leftmost square in column 2i, so in an even numbered column. We want to show that this sum is less than 30h. 50h. 30h.
30.
30h, that's it. Okay, let's proceed. So now, again, we're assuming that the game was not lost before gamma. Because otherwise, this is trivial. We're not even really having this discussion. So, we have this result. Can anybody try and interpret this for me? So, just quickly what this is saying, I'll interpret it, and then maybe someone can give me a justification. We're saying that the number of pieces placed in column DI minus the number of pieces placed in number of squares placed in column DI plus 1 must be less than or equal to H. Anybody got any idea why this must be true? Like, what would be the consequence if,
A lost game.
Yeah, exactly, right? So if you had more than, H cells in one column, like so if this difference was more than H, so you've got a column here, and you've got some kind of column here, then in particular, the larger one must be breaching the ceiling, so the game's lost. So we have that inequality, which is quite nice. Okay. Similarly, if the game is not lost during gamma, this one is a little bit more tedious, I know, but it's the same idea. The number of pieces placed in cell in column I plus 1 is the number of pieces placed before gamma plus the number of squares placed during gamma, and similarly the number of pieces, the number of squares placed in column I is just di plus the number of squares placed during gamma. So that's where this inequality has come from. And for the same reason as the last inequality, this must also be less than H, less than or equal to H. And so with a little bit of rearrangement, we find the following, which gives us this inequality. So in particular, we've just shifted this across, used the previous inequality to turn that into H, and now we get di plus 1 minus di is less than or equal to H. Something nice about this part of the proof is that we now say goodbye to di. So in essence, we no longer care about the pieces that were placed before gamma. So now we're just looking at placements that happen during gamma. Okay. So now we derive a formula, or we write down a formula for di. So if we want to think about the number of squares that have been placed in column di, well, we just have to think about the possible placements that can contribute to column di. So in particular, if we place a piece vertically in column I minus 1, then the rightmost part of that piece must be in column I. And because it's vertical, there are two set of pieces, and so we have 2di minus 1. For the same reason, if a piece is placed vertically with its leftmost squares in column I, well then obviously it's going to have two pieces. Similarly, if we place a piece horizontally centered to the left of column I, then we're going to get exactly 1. If we place it centered in column I, we're going to get 2, because of this little lump in the middle of it. And lastly, if we place one to the right, we're going to get exactly 1. So this is a formula for the number of squares placed in column I in terms of the placements of the pieces. So we get the following difference, and this is just some algebra. I won't explain this one, but move on. Okay, so from the inequality proved a few slides ago, we know that this difference must be less than or equal to 2h. And what's nice about this difference is that it exhibits some symmetry. So in particular, if we separate it into its positive and negative parts, so in particular we move all the negative parts to the right side of the inequality, we have this sum of 3 terms, and on the right-hand side of the inequality we have this sum of 3 terms. But this is exactly the same set of terms, just with I substituted for I minus 2. So that's quite nice. So we're going to do a little bit of induction, not formally, so no formal induction proof here, but we're just going to induct casually to derive a nice little inequality. So in particular, if you take I equals 1, then we have, with I equals 1, we have 2v2 plus, and the camera see me?
Yeah.
Plus h3 plus h4 less than or equal to 2h plus 2v1. Yeah, 2v0, that's right. 2v0 plus h1 plus h0. Can anyone tell me why these terms are 0? Just recall the definitions of the terms. So
Oh, yes, because there's a 0. There's no 0 column
yeah, correct,
as a
exactly,
first
right?
column.
So we started indexing from 1, So there are no pieces, so we immediately get rid of these. There's no pieces placed in column 0, column 0 doesn't exist. Similarly, we can't have a piece centered in column H1 because then it's got a piece in column 0. So in particular, we have that 2v2 plus h2 plus h3 is also equal to 2h, which is quite nice. And now we use the induction image. So in each case, we have that the sum of the next 3 terms is equal to less or equal to 2h plus the sum of the previous 3 terms. We know that the first 3 terms are less than or equal to 2h. So the second 3 terms are less than 4h. The third 3 terms are less than 2h plus 4h is 6h. So on and so forth. We derive this inequality. So I didn't want to get too bogged down in the weeds of the algebra, but it's a nice little exercise yourself just to prove this. Okay, and the slides will be available after the talk. You can go through it. Okay, so now what we have by chaining these inequalities together and just summing them is we have that 2v2 plus 2v4 plus etc. plus 2v10 plus h2 plus h3 plus dot 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 plus h10 is less than or equal to 2h plus 4h plus dot 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 plus 10h. Okay, just by chaining each of those generalized inequalities. Now we've already grouped the terms, so we just factorize out a 2 in front of the two k terms, and we've sneakily added k equals 1, even though we don't have it in the h sum up there. Anyone know why that is? Why are we allowed to do that? Why can I just chuck in h1?
Because it's 0.
Because it's 0. You're always allowed to add 0. Should be one of your favorite tricks. So we've added in that, and now we have exactly the result we wanted. Well, not quite. We have 2 times the sum of the even of the columns, vertical columns, plus the sum of the horizontally placed ones. It's less than 30h. But because the vi are all positive terms, we can literally just delete one copy, and we've only made this side smaller, and the inequality holds. Great. Even though I know intuitively, if I were playing Tetris, that the number of such places, I would try to avoid placing pieces in this way. It's a little bit unintuitive to me that there is this fixed number out there somewhere in the vast mathematics of Tetris that prevents me from placing more than this number of pieces in this way. That's kind of an interesting fact to me, but in essence, if you kept doing it, you would just breach the ceiling. Remember, that's where the bounded area inequalities came from, right? The only thing we mandated was that we can't breach the ceiling. And so to get these inequalities, it must come from the fact that we can't breach the ceiling. Anyway, just a side note, not too important. So now we end up with this position where we can only place pieces vertically such that their leftmost pieces are in an odd numbered column. Okay? So that's going to lead to the formation of towers. In essence, what we're going to have is we're going to be able to stack pieces either by placing them here, with the leftmost column here, 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 and there's actually one more column. I just have blocked to draw. I'll show you a picture now. Okay, so this is what happens when you can only place pieces with their leftmost cell in an odd column. You end up with this kind of structure. There are 5 such columns. This is going to be critical. The fact that it's odd means that we're going to have some kind of parity argument where one parity must be larger than the other. I'll explain what I mean. We will call a column left if its topmost piece is left-oriented. We will call a column right if its topmost piece is right-oriented. Or rather, I'll fix this up before I submit it. So in this example, we have 2 left columns and 3 right columns. Okay? So when I refer to the parity of a column, I mean is it left or is it right? Cool. Lemma. In a sequence of 12H placements, a column will have to be capped with a piece of opposite parity. The idea here is that eventually, and maybe you can see why just by looking at this picture, but eventually you're going to have to swap one of these columns. One of these columns is going to have to be replaced with a cap of the opposite parity. What's really going on is that if you have 3 of these columns and you have to distribute the appropriate pieces to this set of 3 columns, they're going to grow slower than this one because you're only dividing between 2 columns. So you can see on the board here that this column is growing quite quickly, and this piece coming down is bound to eventually end here because we can't place it up there anymore. Okay, and this is problematic. One implicit assumption I made is that we've already made all the 30H placements. So we are assuming at this point in the game that we are no longer allowed to make odd placements. Why can we assume this? Well, we know that there are a finite number, so we can say that if your strategy involves, placing more of these pieces, fine, I don't care. Get me to a point where you've finished placing all those pieces, because you can only place so many. And I will assume now that you are no longer making any of those placements. because otherwise I would just have jumped further on. Okay. So, in a sequence of 12 H placements, a column will have to be capped with a piece of opposite parity. So where does this number come from? Well, it comes from a few applications of the pigeonhole principle, in essence. So by the pigeonhole principle, there will be either at least 3 left columns or at least 3 right columns. This is because there are an odd number of columns, so one of them has to have a majority, a strict majority. Without loss of generality, we will assume the majority of them are left. So in my picture, I think I've actually done the opposite. Doesn't really matter. So I guess we're just calling these ones left, these ones right. Although your choice here is somewhat arbitrary. Okay. So if I drop 12 H pieces, exactly 6 H of them will be left, and exactly 6 H of them will be right. Because recall, it's just an alternating sequence. So again, by the pigeonhole principle, one of the right columns will receive at least 6 H pieces. This is because there are 6 H right pieces. Oh, sorry, that should be 3 H pieces. No, that's right. I think I made a slight mistake here. Not actually, but just in the presentation. I think in particular this number should be 3H for the top ones and 2H for the left ones. Okay. I guess you're going to have to do this with the board. So we have 6H right pieces, which means at least 3H of them. Yes, this is correct. 3H of them must belong to one of the tails. Now we have 6H of the left pieces. By the pigeonhole principle, at least one of them will have to receive less than or equal to 2/3 of 6H, sorry, 1/3 of 6H, which is 2H. So yes, in particular, we should have 3H and 2H, my bad. The difference in height between these columns will be grown by 2H. Sorry, I was a bit late when I finished writing this. So why is this the case? Well, one of them is going to receive 3H pieces. Okay? So that means it's going to receive, 3H vertically placed pieces, which means it's going to grow in height by 6H. Meanwhile, this one is only going to receive 2H pieces, which means it will grow in height by 4H. So the difference is 2H. So in particular, after 12 H such placements, we're going to have a breach, so we have to break this chain. So what happens if we break the chain? What happens if we, reverse the paradigm? If I shuffle this piece down here, I hope everyone can see that there's going to be a little gap of 2 left there and there. Yeah. So in particular, if you stack pieces like so, and you try and put one like this, can I draw? Sort of. Oh. Yeah, that'll do. Yeah. You end up with this gap in the middle, which is a problem. Now, these gaps can't be filled. Why can't we fill those gaps? Can you
It's blocked.
Sorry?
Because it's blocked.
Well, yeah, but maybe, what if I just, what if I just put in a piece like this? What's wrong with that?
Because we're not aligning the horizontal pieces.
Exactly.
Yeah.
The odd placement lemma guarantees that we're no longer allowed to place pieces like this. So these holes are gone. You could think that maybe also you could try and fill it like this, with but this is also prohibited by the lemma, because then if this is an even numbered column, an odd numbered column, this is an even numbered column. So these holes aren't gone anymore. And so once we produce enough of these holes, we can't really place pieces anymore. And so the question is, how many of these holes do we need to fill up the whole board? Well, if your board is, 10 wide by h high, actually I think the camera's facing that way. If your board is 10 wide by h high, you have 10h possible squares, but each gap is 2 pieces. So we have 5h gaps that we can tolerate at most. So if it takes 12h pieces to create each hole, and we need 5h holes, after 60h squared pieces, or placements, the board's going to be, done. You're not going to be able to place equal pieces. That's the end of the book. So let's just have a look at this formally. Yep, this is what we just described. After 5h such gaps, the board is void, and after at most 60 squared plus 30h squared plus 30h placements, the game is over. Why do we have to have 30h?
For the original.
The odd placement number. So we know that after at most, we can have at most 30h of those pieces, and then otherwise we have these different placements. That's good. Okay, so that proves our result. Why is this 30h squared plus 15h?
Symmetry?
Not quite. It's because there are two pieces here.
Oh.
So this result is in terms of total number of pieces,
Oh.
but this sequence of two pieces is two pieces long. So,
Okay.
so after you have this sequence of, yes, length 60h plus 30h, you're not going to be able to play anymore. Game's over.
Interesting.
That's a lot. The paper that I basically ripped this proof from doesn't have provide any kind of lower bounds. It doesn't say that, beyond this point, no matter how many pieces you get up to this point, no matter what they are, how crappy they are, you're going to be okay. Similarly, it doesn't really provide any tighter upper bounds. It doesn't prove the optimality of the bounds provided. So these are really open problems, and frankly, they're unlikely to be solved. Depends on a few things like not quite the distribution. If you allow any distribution, then it doesn't matter. But this is the main result of the talk. But now I suggest that even though we have to get this crazy pathologically unlikely sequence to end the game, I claim that, well, it's probably going to happen. And when I say probably, I mean it's almost surely going to happen, in the sense that the probability is literally 1. But what does that really mean? Okay, so I think we have a bit of a problem if we try and talk about probabilities of infinite sequences. So that's my conjecture. So my conjecture, my claim. So let's think about some finite sequences for a second. So suppose now I'm flipping a coin. Can you guys see this button?
Yeah.
Suppose I'm flipping a coin, and I ask you what's the probability of getting the sequence heads, tails, heads? I hope it's pretty obvious that it's one over 8, or 1 over 2 cubed. Similarly, we have, probability of getting 2 tails is 1 over 4. More generally, if you have a sequence of length n, the probability of getting any particular sequence is 1 to the n. Okay. Then what does it mean to have the probability of an infinite sequence? I claim that this is well defined, and maybe you have some intuition for what a particular sequence, the probability of a particular sequence should be. So, what if I ask you for the probability that I flip a coin infinitely, and all I get are heads? What are the chances? 0? Yeah? I think it's pretty unlikely, right?
Yeah.
Okay. Now, there's no real reason why that sequence should be different from this sequence. I mean, really? You're going to keep getting heads, tails? This is also 0. But we don't really have a good way to determine, or to think of generally, formally anyway, a good formal argument for why these probabilities are 0. You can come up with some heuristic ones, but they do essentially use the principles we're going to discuss here. And so we'll basically get into that now. So, the key idea when thinking about probabilities that are a little bit harder to wrangle, so maybe things where you have an infinite sample space, are to no longer think of probabilities of individual events, but to think about probabilities of sets of events. Okay. So for instance, if I have a set of outcomes, I'll explain this here in a minute. So if I have a set of outcomes, a set of events, and it's contained in another set of events, I can make a pretty natural statement, which is that the probability of something of one of the events of A happening is less than or equal to the probability of one of the events of B happening. What do I mean by this? Well, suppose I think about this set of events. Okay? I flip a coin a different number of times, but now I'm thinking about all the sets of events where the first 2 flips are H. So it could look like H, H, T, H, whatever. I don't really care what happens after the first 2. It could be any infinite number of things possible. But now I'll also think about the sequence, or the set of sequences, where the first flip is heads, and I don't care what I get afterwards. Which one of these things should be more likely?
Second one?
Second one. Why?
Because there's infinitely many versions of it.
Well, there are also infinitely many versions of this one too, right? But I guess the key is that if this happens, then this also happens.
Yeah.
Okay? So we say that basically the set of outcomes B contains the set of outcomes A. Okay? So the set of these outcomes includes the set of this outcomes. Okay? Right? So basically, why do I do the inclusion in that order? Well, any of these belongs to this, which means that this is inside this, if that makes sense. Okay. So logically, we come to the conclusion that the probability of A should be less than or equal to the probability of B. So in this specific example, the probability that the first two flips on H should be less than the probability that the first flip is heads. Can anybody give me some probabilities, like what they think these numbers are? What should the probability that the first flip is head be?
Half.
Okay. And this one?
Quarter.
Quarter? Good. And in fact, a quarter is less than half. So it's always good to check the equation.
Good.
Okay. So now I can think about, now we have this kind of tool, this idea that if one set includes another set, the probability should follow the same relation. We can start thinking about how to think of the probability of this. Okay. So, I'm going to claim that the probability that the probability of getting this sequence is less than or equal to the probability of getting a sequence that starts with a head. Let me write this out. Okay. So, this is not just one sequence, it's a set of sequences. It's the set of all sequences that start with a head. I claim that this sequence, or this set of sequences, contains this sequence. I hope that's obvious. And so, we should have this relationship, right? So the probability should be less than or equal to half. Okay? But also, this set of sequences contains this set of sequences, this sequence. So in fact, we can go a bit further and say this. But in fact, we can extend this as far as we like. And so we get the following set of inequalities. Now for any choice of n greater than or equal to 1, we have this result. H. And in fact, it doesn't really matter what I choose n to be. And so it follows, by squeeze lemma, whatever you like, that if, well, let's just think about it this way. The probability has to be greater than or equal to 0. But if you tell me it's some number bigger than 0, I'll crank up n really high and I'll laugh in your face. And so the answer has to be 0. So the probability of any particular sequence, doesn't matter which sequence, by the same argument, is exactly 0. So you will learn about this at some point if you take measure theory, which is a class I highly recommend. But in the meantime, let's turn it back to our particular problem. So let Pn be independent random variables, sorry for the terminology, uniformly distributed on the set of tetrominoes. So if you remember our set of tetrominoes from earlier, we're going to say that the random variable, Pn, is, Pn of x omega, equals notation. It's going to be in this set of Tetris pieces. So it's going to be a square, these, or one of those, etc. It's going to come randomly from this set. Okay? Now, our choice here is independent for each pi. So, the value of the first Tetris piece does not affect the value of the second Tetris piece. These are all just like, there is some positive probability of each one, doesn't really matter. And so now we want to think about, in the same way we thought about sequences of head flips, we're now thinking about sequences of tetromino pieces. What is the probability that eventually we hit the sequence gamma? Now I'm not saying what is the probability we start with gamma, or that some set of pieces at some particular point is gamma. We're saying that at any point, we're looking for the probability that at any point I hit gamma. Okay. So here's our approach. We're going to set L to 60h squared plus 30h, which is the length of gamma. And then we're going to partition the infinite sequence. We'll go back to P now. Okay. So we're going to think about this in chunks. So we have the first two pieces. Okay. The first L pieces. Then we have the next L pieces. Okay. And so on and so forth. We have all these sets. Okay? Now, I claim that these partition piece generations, or whatever you want to call them, these like random pieces, are all picked independently. So the values inside here do not affect the values inside here, do not affect the values inside here. Okay. So, what is the probability that this sequence is exactly gamma? You don't have to come up with an exact number, but like, how can we think about this? How can we think about the probability that this set of pieces is exactly gamma? Sure.
1 on the number of possible pieces to the power of the length of gamma.
So in theory, you should have some kind of probability that this is gamma, which will be, 1 on 7, which is the length of gamma, which is like that, right? That's why we chose it to be that, right? Okay, great. So the probability that we get gamma, it's not 0. It's really small. Like, I cannot stress you like how small this number is. Like, Python would tell you this number is 0. But, well, for any sensible choice of page. But it's not 0. And so critically, 1 minus p, we'll call it q, is not 1. Okay? In fact, q, the probability that I do not get gamma, is less than 1. Okay. So, now we we'll actually keep this last part. One last part to finish this off. Actually, no, we use the board. It's fine. So, let's call the event En, the event in which the pieces PNL plus 1, PNL plus 2, etc., Pn plus 1L are not gamma. We know that the probability that this is the case is Q. Well, we said P. Say P. I don't know that I want to use this notation anymore. It's good. It works, but it's a bit heavy-handed. So E1 is the set of E1 is the set of all sequences in which the first L pieces are not gamma. E2 is the set of sequences in which the second 2 L pieces are not gamma, etc. Okay? So I guess we can introduce one more result that we don't like, which is that the probability of the intersection is equal to the product of the probabilities. Does anyone know why that might be? Does that seem familiar to anyone?
Yeah.
Why?
Because they're independent.
They are independent, right? And that's because we mentioned that earlier. So the result I'm kind of admitting here is that if you have a whole bunch of events and they're independent, the probability that you have the intersection of the events, or some event contained in the intersection of this set of events, is exactly equal to the product of the probability of the events. So the probability that we live in the set of sequences in which the first set is not, sorry, the first L pieces are not gamma, the second set is not gamma, the third set is not gamma, all the way up to the nth set is not gamma, is exactly equal to the product that any individual one is not gamma, which is equal to e to the n. As we crank up n to infinity, this limit is going to 0. But that's not exactly the result we wanted. So what we exactly wanted was that we're going to get gamma almost short. But what this is saying is that the probability that none of these sets, none of these L placements are gamma, is 0. So in fact, not only have we shown that, yes, almost surely, we will see gamma, we've shown that almost surely it'll show up in one of these nice little blocks. It'll show up in either block 1 to L, or block L plus 1 to 2L, etc. Because we've shown that the probability that it shows up in none of these is 0. So the complement must have probability 1, so it must show up in one of these sets. I guess that's what I get for deciding to off-road the final section of my talk, but yeah. At the very least, I hope it's clear why Tetris is a lost game if you encounter gamma. Intuitively, it may be a bit more difficult to see why gamma is coming almost surely. Anyway, that's more or less all I have for you today. Thank you for your time. Any questions? What time is it?
45.
45? Okay. Sorry, I went a little bit further. That's all right.
That's good.
Sorry, I off-roaded a bit at the end. Questions?
So you said they didn't provide like an optimal lower bound for like a lost game.
Yep.
This is quadratic in H. Do you know if they talked about whether you can get something
It's like
quadratic?
asymptotically if we can get that up.
Yeah.
They don't. In the paper, they don't talk about asymptotic lower bounds. I feel like it's somewhat trivial to show that it's linear, at least. Well, sorry, not that it's linear, that it has to be at least linear. It can't be lower than linear, right?
Right.
Like you're not going to get like some logarithmic number of pieces in your game,
yeah.
right? Because the ball is like fundamentally.
Yes.
So like I guess we're at O of like 2L, sorry, H squared. You're asking if we could do better.
Yeah.
We're not going to do better than O of H.
Yeah.
But where exactly we live in between? No idea. My suspicion is that I can't see any reason why it should be something like neurotic, like square root of H to the 1.5. But you never know, we always get some like crazy bounce off the nowhere.
Yeah,
Maybe
yeah.
there is some constant such that this is exactly equal to like 1 plus, I don't know what you call this constant, like not epsilon, phi. Maybe there's some constant phi, so that's what we got, but no, they don't talk about it. But
Because it's quadratic, because it's like a two-step process kind of thing.
yeah, I guess, I mean, the quadratic part only comes from the tower process. So if you can
Yeah.
somehow find a different reason why this alternating set is going to break that doesn't require you to have a quadratic number of pieces placed, then I'm sure you could. But my knowledge not. I guess you could also introduce another term here where that would also be linear in like W for each one. If you're allowing the width of there. But we're not doing that. But yeah, so that's kind of the state of the art. There's not too much known. Any other questions?
Why does the argument fail if it's not congruent to 2 mod 4? Like what if it's congruent to 0?
Oh, because if it's just a straight like multiple of 4,
Yeah.
then you can just have like alternating. You can have 3 columns on either side,
Oh, so
and
you
then you
get
get
them
an odd
evenly
thing in the middle,
distributed.
and then you can switch them
Oh, yes,
evenly
of
and
course,
go
yeah.
up each time. So you can just generate a quick pattern which fills the space evenly.
Yeah, that's the idea. So you need these towers to grow at different rates.
Right, and then that's where you get the
That's what breaks.
difference in 3 and 2 from vision.
So just go back to that diagram real quick. You can kind of see it here, right?
Like if you had a third tower, you could just grow them up next to each other and it'd be fine.
Well, it's probably not fine, but like it's hard to prove that it's not fine.
I mean, if you got an alternating sequence, you can do like left, right, left, right, left, right. Middle row's gone, left, right, left, right, left, right. Middle row's gone, left, right, left, right, left,
So
right.
the specific
Forever.
I see what you're saying. Yeah, I see what you're saying.
It wouldn't matter.
So do you reckon there's a different sequence in where perhaps it could work? Because so we need congruent 2 for this gamma, but is there another one?
This is a remarkably simple proof. Like, given how like ugly this problem is, like it's kind of nice that there is this kind of sequence which just breaks it very easily for us.
But it's kind of the natural sequence to go with, though.
Yeah, exactly.
Because the zigzag pieces are the ones that are always
Yeah, if
annoying.
you play Tetris, it's a very natural thing, which I think is a nice part about this is that, okay, maybe some of the steps seem like they've fallen out of the sky, but at the very least, I think everyone can appreciate that, like, this is a really bad sequence. Like, this is not going to be much fun to play. And so maybe you can conjecture that, yeah, probably this will ruin my game. And in fact, it does. Yeah. But no, I think, I don't know, I feel like all the other pieces play too nicely together. I feel like if you were to start throwing in things like the squares or the T pieces into the mix, that they would just like kind of gel.
So you're conjecturing that if you've got like an even number of 2 columns,
Yeah.
then perhaps you can always
divisible
win.
by 4. If the number of columns
Yeah,
is divisible by
yeah,
4,
yeah, yeah.
yes, I am conjecturing that, yeah, maybe
You can always
game is
win.
equal. If you really wanted to show it, you could probably just brute force it. In the sense of like, you could find some kind of like, you can find some number like L, some arbitrarily large number L, such that after any L pieces, the board is clear.
Yep.
There are some obviously some constraints you place upon L, because like for instance, if the board is clear, like there are no pieces on it, then you have to be like an even number of the, you have to place an even number of like, the number of squares you place has to be an even number of the squares you place. Yes. Totally. I guess it doesn't really matter. So I guess if you place, if your number of columns is divisible by 4, then no, you do get this result. Okay, what I'm saying, one more time, is that if you have, say, 4k columns, then you have to have a multiple of k pieces.
Yeah.
And that's because the number of, the length of each row has to divide the number of squares placed, which is like, 4 L, or 4p. So that requires p divides k, or k divides p. Yeah, so that is my conjecture, I guess.
Cool.
But, and I think it is possible to prove it. I think it'll just be a very ugly computer proof.
Right.
Any other questions?
I think we can continue questions over pizza, but thanks so
No.
much for talking.
Yeah.
Sorry, we're not going to